Okay, higher level, we're going to look at partial fraction decomposition. Sounds quite difficult. It's not that bad, as long as you're comfortable with fractions. We're only going to be looking at where the denominator is a quadratic and the numerator is a constant or a linear, so of a lower degree. There are some that you can't technically do and some that are more complicated, but this is all we're going to see now. So what I say does apply to that, although you can conceptually kind of expand that if you ever need to. So you'll be given something like this quite often, and it will help, or it can be helpful, depending on what you're doing, to look at it as these partial fractions, where you take a more complicated fraction and decompose it, break it up into its pieces, where you have a constant over linear plus or minus another constant over another linear. This could be the same if you have something that's a perfect square. You could have multiple if you're looking at things that are not quadratics, etc. And this line, these three lines, I should say, means identity or is the same as. So it's essentially equal, but not necessarily a solution. So I go back and forth on those. I do apologize. It's supposed to be is the same as is the same as. And when we solve, we would use an equal sign, but it can be thought of as the same thing, really. So the first thing I'm going to do is use the method that the book does, and that's pretty useful for some of the simpler ones. Although you can use it in any, I just don't like fractions quite as much. So what we're going to do is we're going to try to break this down, and the first thing you need to do for that is to figure out how we're going to factor this. Now, if you don't remember how to factor, I'm going to do it quite quickly here. We can take a look at that again. I can put a link to do that, and the next one will be more challenging, so that might be good to review as well. And since there's nothing in front of the x squared, it's actually quite easy. I'm just going to find the two numbers that multiply to -2 and add to -1, and those are -2 and 1. So I'm going to rewrite this fraction that I was given in the factored denominator form. So x, I said -2, and x plus 1. Now what I'm going to want to do is I'm going to try to find the constants that will do this. And I know as I'm going through that I can write two fractions where the bottom of one is x minus 2 and the denominator of the other one is x plus 1. The order doesn't matter here. And these are going to be equal to some constants, some numbers up here. Now, if I were to want to write these over the same denominator so that I could actually add them, I would have to multiply both the numerator and the denominator of this by x plus 1, and I would need to do both the numerator and the denominator of this one by x minus 2 so that I'd have balanced fractions with a common denominator. And one way I'll actually do that, I'll say here, well, it's actually looking a little bit more complicated. I could have written this to make it clear in the last step. Okay, and I can do that same thing. Oops, that's minus. Doesn't matter the order. But of course, to keep this one balanced, I would have to multiply both the numerator and the denominator. Now, the denominators have been equal the whole way through, and I don't have anything I need to solve for. But what I want to do now is look at the numerators here, and I want to make them equal 5x minus 4. I'm going to no longer consider the denominator. The denominator was just to figure out what kinds of coefficients are here. So now that I'm looking at the numerator, I'm going to be able to solve equals a x plus 1 and b x plus 2. And I'm going to do this using really convenient values. That's what the book does. So the values that I'm going to use are -1, and oops, helps if I actually write this down correctly, -2, and +2. The reason being that when this is -1, a is gone, because a times 0 is 0, and I only have something with b left. And when this is 2 and x is 2, this is 0, so I'll only have something with a. So the values I want to do, let's try when x is -1, and let's try also where x is 2. So when x is -1, I'm going to put that in here and here on the left and on the right. So 5x minus 4 when x is -1, -5 minus 4 is negative 9 equals a times 0 plus b times a negative 1 minus 2 is negative 3. So negative 9, a times 0 is gone, equals, of course, minus 3b. So b equals 3. And I'm going to do the same thing now with x being 2. So when x is 2 and I put this in, well, 5 times 2 is 10, minus 4 is 6. And when I put in 2 over here, I get, and of course that will be gone now, so I know 6 is equal to 3a, so 2 is a. From this, I now have the values that I want, and that is that a is 3, so 2 over x minus 2 plus plus 3 over x plus 1. So here's my final answer. By breaking down, again, the denominator into its factors and finding the values of a and b that I can multiply to get the numerator. And I just checked these convenient values here. Now, I'm going to look at one that's a little bit trickier, and I'm going to show you another method. It's up to you to decide which one you want to do. They both work out really well. The first thing I need to do is factor the denominator here. I'm going to do that up here where there's just a little bit of space. Remember that to factor these quadratics where there's a coefficient of x squared other than 1, you need to multiply the a times c, so 3 times 8 is 24. And I'm going to look for the two pairs that multiply to 24 and add to 14. And that's 12 and 2. So ax squared and c can go in, and I've found the pair that I want as my x's that would have added together in the FOILing. And now I'm going to take out the greatest common denominator of each. So 4 out of there. I don't have any issues with negatives in this case, but it is something to watch out for. So 3x plus 2 and x plus 4. So negative 8x minus 2 over x plus 4, 3x plus 2. And again, we want to be able to break this down in something over x plus 4 equals something else over 3x plus 2. So when I do all of this here, I can first think of it as a, for example, times x plus 4. Okay, I'm doing this in the opposite direction of the last one here, but that's also kind of fine here to show you what I want. These are now two separate fractions. I broke them down with the a and b, and these would cancel and be my a over 3x plus 2, and I'm going to write that again in a second. And this would cancel then, just to look at both of them. That's the same thing as saying a over 3x plus 2 and b over x plus 4. Now, I know that this here, I could have written that again as one fraction, is going to be negative 8x minus 2. So negative 8x minus 2 is equal to a, x plus 4, and b, 3x plus 2. And I'm going to multiply this out to create a nice system of equations. So negative 8x minus 2, ax plus 4a plus 3bx plus 2b. Rearranging it so that I get my x terms together, so ax and 3bx. And then I'm going to get my constants together. Remember that a and b are actually some numbers, so those are constants and not variables. And when I factor out x here, I'm going to get the coefficient of here. And this, I don't need the parentheses, but I'm going to use it, is going to be negative 2. So the negative 8 needs to equal a plus 3b. And negative 2 is my constant here. and I'm going to create this system of equations. So I know that negative 8 equals a plus 3b, and I know negative 2 is 4a plus 2b. And I'm going to now use a system of linear equations here to simplify this and solve for a and b. And this is set up quite nicely to solve using elimination. I do need to multiply one of these in order to get one of them gone. And I will pick multiplying this top one by negative 4. It doesn't matter. If you do need to review that, I'll post a link to that. In order to have that happen well, though, I want to multiply this by negative 4. That's going to give me 32 equals negative 4a minus 12b. This one I didn't need to do anything to. And the goal of doing this, again, if you don't remember how to do that, is to get variables that will cancel out. Oops, let me move that over so you can see it. And I'm going to add straight down. So 32 minus 2 is 30. Negative 4a and 4a makes the a's go away. And negative 12b plus 2b gives us negative 10b. And when I solve that, I get that b is negative 3. I can also now go back to any of the equations I've used to find out what a is. I now know that b is negative 3. And when I simplify this and solve this, I get that a is 1. So here's the other value. That means that this, okay, I'm going back up here. I'm going to leave that like that though so you can see it. Now we can see everything. When I substitute in the values 1 over 3x plus 2, and I'm going to put the minus in front so that we don't have plus a negative number, x plus 4. And that would be our final decomposed fraction. In just a second, I need to find the other paper that's missing. The question is, why might we need to do this? So it's just a quick thing here. We are going to use a lot of this in calculus, but to think of this as graphs, I have both of my decomposed fractions sketched here. I even flipped this one around already to be a negative 1 so that it's already reflected and I don't have to look at subtracting. And what I think about as I add these, I'm going to look and see where things are changing and where things are not. So if I look at this right here, for example, the end behavior here of this 3 over x plus 2 is going towards 0, and this is as well. Okay, so both the horizontal asymptotes are at 0, so I'm still going to have the 0. 0 plus 0 is 0. If I look at these points here, I can add at the x values. So there's nothing at, I'm going to have the same asymptotes. I should have said that first. My asymptotes are going to be at negative 2 because the first one has an asymptote at negative 2. And at 1, that was kind of funky here. And at 1. So I have 2 asymptotes because there are 2 problems with x here. In both cases, they're going to be approaching 0. And when I add things, for example, like what's happening here, if I look right here, when x is at 1, I'm at 3, and when x is at 1, I'm at 1, so 3, 4. So I'm going to be able to plot all of these points on here. And by doing that, I'll be able to check out what's happening at each particular thing here. So I notice that this is going to negative infinity at negative 2, and this is really close to 0. So this is actually also going to be going to negative infinity. When I add negative infinity and 0, it's going to be down here. When I look at this asymptote here from this side, I see that I'm pretty close to 0 here. There's going to be a slight change, but we can get the general idea of the sketch. So at 2 at this, 1 at this other asymptote, it's still quite a low number. So negative infinity again. So when I approach this, I'm coming down from this side. And when I look in this middle, these are both positive numbers. And whenever I'm going to 0, it's not doing much. So right here, I'll be able to see this is approaching positive infinity at my asymptote, and this little bit of extra is not going to do much. As I get closer to this other asymptote, I have essentially what's going to 0 and this really big number going to positive infinity. So I'm able to use the ideas of where it's going to infinity to sketch approximately where this is going to be. We can check that with a graph.